A vector can represent a point or an arrow in the two-dimensional plane, or in the 3D space. In this case, we use a three-dimensional vector. Regardless of the position of the point or the tail of the arrow, we can always represent it with a vector. In high school math, we've seen vectors up to 3D, but a vector can have an arbitrary number of dimensions. We usually call the vertical matrix a vector, but not a horizontal one. Instead, we call it a row vector. To write a vector horizontally, we use parentheses. So these two notations represent the same thing. Other than just points and arrows, vectors can represent many other concepts, such as colors, asset allocation, where each entry represents the weight of an asset. An image can also be represented by a vector. This image, for example, can be flattened into a vector. The length of the vector equals the number of pixels in the image. Even a video can be represented by a vector. You see, a video is just a series of frames, so the length of the vector representing it will be the number of frames times the number of pixels of a single frame. Linear algebra has a variety of applications in fields ranging from machine learning, data science, physics, and economics. In this series, I'll be walking through the textbook Linear Algebra Done Right and explain the concept with the help of visualization. In this chapter, we'll be talking about vector spaces. What exactly is a vector space? Before we get into that, I'd like to first introduce some notations that you will run into a lot in linear algebra. First up, we've got univectors. Univectors are the vectors with the ith entry equal to 1 and the other entries equal to 0. We use subscript to denote some entry of a vector. So this notation means this entry, and so it's 1. And this notation represents this entry, so it's 0. Next up, we've got once vector. We use 1 sub n to represent a vector with all the entries equal to 1 and of length n. The subscript is often omitted, so you just write a bold 1 because the length is often implied by the context. 0 vectors are also very common, so we have a notation for it. 0, 0, 0 can just be written as 0 sub 3. Similarly to once vectors, the subscript can also be omitted, leaving us just 0. As an example, in this expression, this 0 is actually not a number, but a vector. We can infer that it's three-dimensional from the context. To build our intuition towards the abstract concept of a vector space, we first look at the more concrete list. A list is just an ordered collection of elements. This is a list. This is also a list. These are all lists. We'll focus on the ones that contain numbers. We use R2 and C3 to denote the sets that contain those lists. You might be wondering, all of the examples we've looked at so far are just elements of Rn and Cn. So do vector spaces always manifest in the form of Rn and Cn? The answer is not necessarily. At the end of the video, you'll have a clear idea why that is. For now, it's fine to think of vectors as lists. Many times we may not want to specify whether we're working with Rn or Cn. In such cases, we just write f to the n. So in the upper example, f equals r and n equals 2. In the second example, f equals c and n equals 3. The notation f actually represents what are called fields. Many of the theorems in linear algebra not only applies for R and C, but also any arbitrary field. But we won't deal with fields other than R and C. So for the purpose of this series, it's fine to just think of it as R or C. To put it very simply, what linear algebra does is just extend addition and multiplication to n dimensions. So let's first try to extend our familiar number addition to Fn. To perform addition in F3, you just perform number addition on each individual entry. And we do the exact same thing for Fn. So that's exactly how we defined addition in Fn. Simple, right? To look at a few examples, if f equals r, we just sum the elements individually. When f equals c, we still sum the elements individually, only that they're complex numbers. Defining addition this way means it's commutative, so changing the order of addition doesn't change the result. To visualize it, putting the blue arrow first, and then the red arrow, and the red arrow first, and then the blue arrow, the sums are exactly the same. Notice how I just used the word define. This is because you can define addition however you want, even in a way that's not commutative. For example, we can define addition like this. It's easy to see it's not commutative. However, this kind of definition doesn't necessarily have the properties that we want, so we won't be using them. So back to the normal definition. With addition out of the way, let's move on to scalar multiplication. What we want to do is multiply a list by a scalar. The lambda here is a member of f. To compute the product, we just multiply each entry by lambda using our familiar number multiplication. So that's the definition of multiplication in Fn. Just to give a few examples, when f equals r, 3 times 1 minus 1 is 3 minus 3, and 0 times 1 minus 1 gives us 0. Note that the 0 here is not a number but a vector. When f equals c, it works pretty much the same way. We just multiply each number individually. Pretty straightforward. Before we get into the next section, I cherry-picked some problems from the text to cover the essential concepts in this section. Feel free to give it a go. Now we've understood how to extend addition and multiplication from 1D to 2D to 3D to an arbitrary number of dimensions. This serves as a pretty good basis for understanding what an abstract vector space is. A vector space is actually just a set over which addition and scalar multiplication are defined. So we'd like to be able to perform these two operations on any elements in a vector space. What does that mean though? Let's first look at addition. If we take any two vectors from a vector space, we want the sum to still be in the vector space. So that's addition. As for multiplication, if we take a random vector from a vector space and a scalar from f, we want the product to still be in the vector space. That's pretty much it. These are the two operations we want to be able to do with elements of the vector space. So we've defined a vector space in a pretty loose way. Now let's look at the actual definition of a vector space. The addition and multiplication defined for a set must have these properties for the set to be a vector space. Let's look at each condition individually. First, we've got commutativity. It means if we've got two vectors u and v, u plus v must equal v plus u. Next up is associativity. Both addition and multiplication need to be associative. Specifically with addition, if we take three vectors u, v, and w, the sum of u and v added to w is equal to the sum of v and w added to v. That's associativity for addition. With multiplication, suppose a and b are random scalars. Then ab is also a scalar. Associativity requires that the product of ab and v must equal v multiplied by b and then multiplied by a. So that's associativity for multiplication. Next up, we've got additive identity. It states that a vector space must have 0 as an element, such that if we take any vector from the vector space and add 0 to it, the result is still the original vector. So if v doesn't have an additive identity, then it's not a valid vector space. Next, we've got additive inverse. It means that for every vector in v, we can find another vector such that they sum up to 0. The next one is multiplicative identity. It means that if we take multiplicative identity from f, in the case of R or C, it's just 1. If we take it and multiply any vector in v by it, it doesn't change the original vector. Lastly, we have distributive properties. It states that a scalar times the sum of two vectors should be equal to adding together both of the vector multiplied by the scalar. The second line states that the sum of two scalars times a vector equals taking the product of the vector and both of the scalars and then taking the sum. It's quite similar to the distributive property of numbers. You might have noticed that these properties are quite similar to the properties of number addition and multiplication. In fact, if we replace all the symbols with numbers, they still all make sense. It's just that we've extended it to a higher dimensional vector space. Now that we've rigorously defined what a vector space is, it's a good time to go back and examine why Fn is a vector space. For example, let's check if additive identity holds for Fn. If we think of Fn as just Rn or Cn, then it's just a list of n numbers. So the list of n zeros must be in Fn. We can simply write it as 0. If we take any vector v and then add to it the 0 we just defined, then the result should look like this. We just add together each individual entry. So the result we get is still v, confirming that the additive identity does exist in Fn. The remaining 5 conditions, of course, all hold for Fn, as you may verify. Remember how we touched on the fact that vector spaces are not just limited to Fn? So let's now look at an actual example. F to the s, it denotes the set of all functions from s to f. We need to first define addition and multiplication for it to be a vector space. For addition, suppose f and g are both members of the set. Then we can define the function f plus g like this. We define f plus g of x to be the sum of f of x and g of x. So that's it for addition. Pretty simple. Next up, we've got scalar multiplication. Suppose lambda is taken from f. Then we define lambda f of x to be lambda times f of x. Under these definitions of addition and multiplication, f to the s is a valid vector space. Let's use a more concrete example to wrap our heads around it. Suppose s contains 1, 2, and 3. And then suppose f is a function mapping 1 to 5, 2 to 2, and 3 to 4. Then it's easy to see f is a member of f to the s. And then we suppose g is another function mapping 1 to 1, 2 to 2, and 3 to 3, and that h is a function that maps everything to 0. Then we can denote this h by 0. Notice that h is the additive identity, because adding either f or g or any other function to h gives us the original function. So additive identity does hold for f to the s. Let's also check commutativity. Some simple calculation reveals that f plus g indeed equals g plus f, so commutativity does hold. We've looked at 2 of the conditions for a valid vector space. Feel free to check the other 4. Although what we just looked at is just a special case of S being the set containing 1, 2, 3. F to the S is a vector space whether S is the natural numbers, the real numbers, or any other set. So F to the S in general is a vector space. Lastly, I want to show an example as a simple exercise. We use f to the n by n to denote the set of all n by n matrices. For example, this matrix is a member of F2, 2. And this matrix is a member of F3, 2. Now the question is f to the n by n a vector space? How should we define addition and scalar multiplication for f to the n by n to be a valid vector space? Take a little moment to think about it. I picked some problems for this section as well. Enjoy. Next, we're going to look at what are called subspaces. Suppose V is a vector space and U is a subset of V. Then is U automatically a subspace? Quite obviously, the answer is no, since we call it a subspace. A subset must be a valid vector space to be a subspace. And of course, that's under the same vector addition, scalar multiplication, and additive identity. As an example, if V equals R2, and U is the set containing the point 1, 1, then U is clearly not a subspace. Why? First of all, 0 is not in U, so that's already one condition not met. And if we take 1, 1 and multiply it by 2, the result is not in U either, so it's not closed under multiplication either. It's quite a bit of work to have to check all the 6 conditions for a vector space, isn't it? So let's look at a simpler way to do it. To check if U is a subspace of V, it actually suffices to only check these 3 conditions. First, additive identity must be in U, and U must be closed under addition. So if we take 2 vectors from U, the sum must be in U as well. U also must be closed under scalar multiplication. So any vector in U multiplied by a scalar must still be in U. As long as these conditions are met, U is a valid subspace. Now you might ask, why do these conditions suffice? This can be proven quite simply. We just need to assume U is a valid subspace and prove these 3 conditions hold. And then we assume these 3 conditions hold, and then we prove U is a valid subspace. By doing so, we can prove that these 3 conditions are equivalent to U being a subspace, meaning all the conditions for a vector space hold. I won't delve into details for simplicity here. It's demonstrated very clearly in the original text if you're interested. Now let's look at a few examples of subspaces. Suppose V is F4 and U is the set of all the points satisfying this equation. Now is U a valid subspace of V? The answer is it's only a subspace if B equals 0. To prove it, we need to first suppose U is a subspace, and then prove B equals 0, and then prove the other direction by setting B to 0, and then prove U is a subspace. So we need to show it has 0, it's closed under addition, and closed under scalar multiplication. Once we've shown all of those, we will have proven U is a subspace. I'll leave the actual proof as an exercise. Now let's look at another one. Let's suppose V is R to the R, so it contains all the functions from R to R. Notice that we're using the same notation as F to the S. We're just changing the F to R and the S to R as well. Now let's define U to be the set containing all the differentiable functions in V. In this case, is U a subspace of V? Again, we need to check these 3 conditions. First of all, we know f of x equals 0 is differentiable, and that its derivative is still 0. So clearly, the additive identity exists in U. Now let's take 2 functions f and g from U. Now since f and g are both differentiable, according to basic calculus, we know that the derivative of their sum equals the sum of their derivatives respectively. So f plus g is clearly differentiable, and therefore it's in U. Now again, we take a function f from U. Then the derivative of a multiple of f is equal to that multiplier times the derivative of f. So U is indeed closed under scalar multiplication. Having proven these 3 conditions, U is indeed a subspace. Next thing we're going to look at is the sum of subspaces. Say V is a vector space, and we have 2 subspaces in it. Then how do we add together these subspaces? First thing that comes to mind might be taking the union. But then you notice that the union of 2 subspaces might not be a valid subspace, so it's not the sum that we want. Then how do we sum subspaces to make the result also a subspace? Let's try to understand via an example. Suppose A is the line on the x-axis, and B is the line on the y-axis, and then we let U be the union. It's easy to see 1, 0 and 0, 1 are both in U. However, the sum of them is not in U, and therefore U is not closed under addition. So U is not a subspace. Now let's change how we sum subspaces. Suppose we take 2 vectors from A and from B respectively. Then we define the set of all possible sums to be the sum of A and B. With this definition of sum, A plus B is actually just R2, as you may verify. Now let's generalize this idea and formally define the sum of subspaces. Suppose we have M subspaces. Then the sum of them is defined as taking a vector from each subspace, then the set containing all the combinations of the vector sums is the sum of the subspaces. That's a definition right there. Among sums of subspaces, there's one special case that we call direct sums. Imagine trying to decompose a vector space V into a sum of subspaces. So that means any vector in V can be written as a sum of vectors taken from each of the subspaces. Now, if every vector in V has only one way to be written as a sum, in this case we call the sum of the subspaces a direct sum. This notation is often used to indicate that the sum is a direct sum. Let's again look at a few examples to deepen our understanding. Let's suppose U is the xy plane and W is the line on the z-axis. Then U and V actually directly sums up to F3. To graph it, let's assume F equals R. Then this yellow plane is U, and this blue line is W. It's easy to see any point has only one way of being written as a sum, and it's always the case no matter where the point is. So F3 is indeed a direct sum of U and W. Let's look at another example. Suppose V1 is the set of all the points with z equal to 0, and V2 the set of points with x and y equal to 0, and V3 the set of points with x equal to 0 and z equal to y. Then the 0 vector can be written as a sum like this, and it can also be written as a sum of 3 0 vectors. So it's clearly not a direct sum. Now we have a pretty clear idea of what a direct sum is. I want to introduce methods to quickly check a direct sum. We claim that if we take 0 from V, and the only way to write it as a sum is by taking zeros from all these subspaces, then the subspaces add up to a direct sum. Now let's try to actually prove it. We need to prove both directions. So we first suppose the sum is a direct sum. This implies there's only one way to write the 0 vector as a sum. And then because we know that 0 exists in every subspace, so taking zeros from each subspace is one way to write 0 as a sum. And we know it's the only sum because of our previous assumption. So writing 0 as a sum of zeros is in fact the unique way to write it, completing one direction of the proof. For the other direction, let's suppose 0 can be uniquely written as a sum by taking 0 from each subspace. Now suppose V is any vector, and that these are two ways to write it as a sum. If we compute the difference of these equations, we get this equation, where each term is a member of one of the subspaces. So this makes it one way to write 0 as a sum. And we already assumed that taking 0 from each subspace is the only way to write 0 as a sum. So each of these terms equals 0. This implies U1 equals V1, U2 equals V2, and so on, which further implies V has only one way to be written as a sum. So these subspaces is indeed a direct sum, completing both directions of the proof. So we've proven that verifying 0 can only be written as a sum of zeros is equivalent to the subspaces being a direct sum. Alright, let's move on to another theorem of the direct sum. U and V intersects at 0 if and only if U plus V is a direct sum. But why is it though? Let's suppose the opposite. We suppose the intersection has a non-zero vector V. Then V can be written as V plus 0, which can be seen as taking V from U and 0 from W. And it can also be seen as taking 0 from U and V from W, giving us two ways to write V as a sum. So it's easy to see if the intersection has a non-zero vector, then you'll have two ways to write it as a sum, making it not a direct sum. Now again, to prove it, we need to prove both directions. Let's first prove the right arrow direction. So we suppose U plus V is a direct sum, and we suppose V is a member of the intersection. then we can infer that minus v is in the intersection as well. And of course 0 is in it too. Then 0 can be written as v plus minus v, where we see v is taken from u and minus v is taken from w. And we know that 0 plus 0 is another sum equal to 0, since we already assume u plus v is a direct sum. We know that v and minus v must equal to 0. Recall that v is just any vector in the intersection, so we've proven the intersection is the 0 set. Now let's do the other direction. We first suppose the intersection is the 0 set. And now what we want to prove is u plus v forms a direct sum. And according to what we've covered previously, we only need to prove 0 plus 0 is the only way to sum to 0. So let's suppose 0 can be written as lowercase u plus w. U taken from capital U and w taken from capital W. What we want to prove is they both equal 0. We first move u to the left side, giving us minus u equals w. As we know, w is in capital W, and so minus u is in capital W as well. This implies u is in w as well. So u is actually in the intersection. And because we've assumed the intersection only contains 0, u equals 0. Plugging this back to our assumption, we have u and w both equal 0. So we've proven 0 plus 0 is the only way to sum up to 0. According to our previous theorem, u plus v is indeed a direct sum, completing the other direction of the proof. Therefore, we've proven that the intersection being the 0 set is equivalent to u plus w being a direct sum. And that concludes this episode. For this section, I picked some problems for the viewers as well. Feel free to give them a go. Okay, we've covered a lot in this video. Let's do a quick summary. We learned what a vector space really is, we learned about subspaces, and we also learned how to sum spaces together. And finally, we learned what a direct sum is. I hope this video was helpful for your learning. If you liked the video, hit the like button to show your support so that I can keep going with this series. Alright, I'll see you guys in the next one.